Okay, so in deriving the curvature tensor, we considered covariant derivatives, two covariant derivatives of a vector field, and now we want to consider three derivatives, the third covariant derivative. But this is going to be too tedious, so we're just going to motivate this. Let's imagine that we're going to we're going to take three covariant derivatives and use the identity due to Bianchi that we derived last time, and we'll end up getting a derivative of this tensor, this curvature tensor, AEBD derivative C, right? Because the other object was the result of two covariant derivatives. So now we have another covariant derivative. Remember, our goal here is to derive the covariant divergence of the rank 2 tensor that belongs on the left-hand side of the field equations for general relativity. And so here we end up getting an AEDC covariant derivative index B plus our AECB index D here, and this is going to add up to 0 using the Bianchi identity that we derived in the previous lecture. So we are a few steps away from getting our object, and so we're going to raise the index here. We're going to get rid of these two indices, AE, bring them up, and then we'll make the indices equal to D and C. Actually, sorry, we'll make them equal to C and B. Well, let's C and B. Yeah. So we'll get to that in a second. Let's raise these two. So we need twice the inverse metric tensor with A's and E's separately. So we need a GA to F and GE to G. So F and G are the choice in this case. We've got A and E were determined by these A and E's. So we're raising this object. Here we have A, E, B, D. We're just repeating this plus R, A, E, D, C, B, B plus R AECB D, and this has to be, of course, 0 still. And so now we have an R F G, because we've raised these two indices to F and G. We still have BD here, and we have covariant derivative C. Here we have an R, AE are gone, they're up now, and so we have FG there as well. We have left DC in B plus R FG. We have left CB, that's in D, and this is equal to 0. And so now we'll contract on this index. So F is B, so F is B, and that gives us R BG BD in C plus R BG DC in B plus R BG CB in D, and that's equal to 0. But we know that given how we contracted here, this is actually, so first of all, we're going to get rid of the common, we're summing on B here, but given which index this is, there's a minus sign here, so we can write this as R G D, right, C plus R BGDC. Here well, we can't do anything here because the B is over on this side, so BGDC B plus, this is a GC, an R, GC, and D, that's equal to 0. Sorry, I said there was a minus sign here, so there's a minus sign here. We've seen this before, and now we'll take G and make it C. G and make that C. Let's see here. G equals C. And this gives us R C DC plus R B. This is now C DC B minus R, that's a C, C D. This is equal to 0. Okay, so now we can sum on C, and we see that these objects are basically the same. So we have an R C D C plus an R B D B, but we are summing on this index, so we call it C in one case and B in the other. It doesn't mean anything. It's the same thing. Minus R C C D. This is equal to 0. Well, let's get another sheet. So we now have, so we can say this is 2R C D C minus R C C D, and that's equal to 0. This is just a scalar. But we want to turn this into an overall covariant derivative, covariant divergence. So we want these indices to be the same. So we need, so this is a minus R, RCC, I'll just call it R, the scalar covariant derivative D. This is, well, it's easier to write this as covariant derivative this way with lowered index, because that way I can use the metric. I can think of raising the index and then lowering the index again to turn it into a C, because that's what I want to do now. If I want to do minus grad D R, well, covariant derivative D, let me raise the index. I have a minus sign, so I'm going to raise, well, I want to turn it into a D, so I'm going to think of this as from a C there of R, we are going to turn it into a D. And so I'm going to raise this using C and some other index, say F, and then I'm going to lower it with an F, right, because it becomes a C, and so an F to a C. Sorry, F, I'm lowering it to a D. What am I doing here? I'm lowering it to a D, and so it goes from C to D in that way. And so I can write this as minus, this is a CD, right, these two, this is the metric and the inverse metric, so I get that kind of an object, del CR, or if we prefer to write it the way we had it before, minus CD R semicolon C. And so the object that we have here is 2R CD minus delta CDR semicolon C, and that's equal to 0. Or we can consider just raising the indices to 2R C and make it, I don't know, an A minus R C, and that has to be G C A, and the covariant divergence of that C is equal to 0. But it would also be true that RCA minus, there's an overall constant here issue. So this is also, the covariant divergence of this is also equal to 0. So there's an overall constant here that we have to then worry about. It'll turn out that this is the object that we want on the left-hand side, and we can figure out perhaps the Newtonian limit. So here we have our object that satisfies the covariant derivative, covariant divergence equals to 0, and this will be set equal to the, in this case it's TCA object, or K.